Alrighty, so this is a Unit 4A algebra practice test. So I'm just going to go through a couple different types of questions that you might see. So the first one is, the function f gives the number of coaches needed on a team that has X players. Explain what this f of 30 equals 2 means in this situation. So when I'm doing these types of problems, I always try to identify what the independent variable is and the dependent. So independent here, okay, is what is kind of negotiable, like what would I be plugging in? And that would be the number of players. So the number of players. And then what depends on the number of players is the number of coaches that they need. Okay, so the number of coaches. So remember, independent is what is in the parentheses, dependent is the output. So 30 independent, so 30 players, means dependent coaches, they need 2 coaches. So let's just see which one lines up here. So when there are 30 coaches, well, that has nothing to do with coaches right here, right? That's talking about players, so not that one. Okay, when there are 30 students, okay, there needs to be 2 coaches. Okay, this should actually say players, but we're going to assume that students are the players, right? There needs to be two coaches, and that does make sense for this one. Okay. Here, there have been 2 coaches for 30 months. Well, this has nothing to do with months, so definitely not that one. And the number of coaches increases by 2 for each of the 30 players. Okay, at no point did it ever say that either, right? Input was players, output was coaches. Okay, so just B. Taking a look at number 2, kind of same thing. The function g gives the weight of a shopping cart in pounds after X items had been added. Okay, so the independent, okay, is what we can control, and that would be the number of items. And then what depends on the number of items is the weight. So the dependent is the weight of the cart. Okay, so independent is in the parentheses, so 40 items means the output, which is the weight, is 62. So 40 items means 62 pounds. So 62 items. Nope, that's not what we're talking about. The weight of the shopping cart has been 62 pounds for the last 40 items. Well, that doesn't make sense. Right? The weight's not going to stay the same the more items you add. The weight of the shopping cart is the same when there were 40 items or 62 items. Again, that does not make sense. But here, the weight of the cart is 62 pounds when there are 40 items. Yep, that is exactly what we had expected. All right, the function g gives the number of gallons of water in the bathtub X minutes after running the water. Write a sentence explaining each of the following equations or expressions in the context. So g of 3. So the input is 3. G of 3 is an output. Okay? It doesn't tell me what the output is, so I can't really say what the output is, but this represents how many, and then the output again is number of gallons. So how many gallons are in the tub after, and then it depends on the input. So the input would be 3, and that's in minutes. So after 3 minutes. Okay, we just can't say what it is. Here, this is the input, and now this time they tell us the output. Okay, and sorry, I should label this up here to be input. Okay, so now I can actually say that after 2 minutes of running the water, okay, so now I know how many gallons are in the tub. So there are 4 gallons of water in the tub. Okay. Down here, the function W gives the number of workers needed at a doggy daycare when there are dogs dropped off. Okay, so here it's sounding like dogs are the input, number of workers is the output. Right? Number of workers depends on how many dogs are dropped off. So again here, 20 is the input. W of 20, the entire thing, is the output. But it does not tell us what it's equal to. So I can't really specify what the output is, but this represents how many, okay, I'm going to talk about the output, which is workers. So how many workers are needed when, okay, my input was 20, and input is number of dogs. So when 20 dogs are dropped off. Okay, down here, input is 30, output is 4. So now I can be really specific. So when 30 dogs are dropped off, okay, the output tells me how many workers are needed. Okay. There needs to be 4 workers. Alrighty, on to the next. So the function G gives the number of gallons of water in the bathtub X minutes after running the water. Use function notation to represent the situation. Okay, so this should sound familiar. It's what we did before. So the number of gallons in the tub is the same. Okay, number of gallons is the output. Is the same, so again, equal after 4 minutes and 15 minutes. These are inputs. Okay, so the function name is G. So G of the input 4 is equal to or the same as G with the input of 15. Okay, again, G of 4 represents an output gallon. G of 15 represents an output gallon. Okay, there are 10 gallons of water. Okay, gallons of water is an output after 5 minutes. Okay, so that's an input. Again, the function name is G. So G of my input of 5 is equal to the output of 10. Okay, and that's all we need. The function W again gives workers after D dogs are dropped off. Same thing as before. So for staff members, remember the staff members were the output when there are 25 dogs dropped off. That is my input. The function name is W. So W of my input, so 25 dogs, is equal to the output, staff, 4. The same amount of staff members are needed, so equals, whether there are 20 dogs or 23 dogs. These are both inputs. So the workers needed when there are 20 dogs, okay, output, is equal to when the input is 23. Okay. Here, functions A and B give the number of people in 2 different cities in thousands who commute to work using public transportation X years after the year 1980. Okay, so which of the following has a greater value, A of 6 or B of 6? They are giving me input. Okay, so I need to put 6 in for X. So A of 6 is equal to, I'm going to plug 6 in right here. So 6 divided by 2 plus 10. Okay, 6 divided by 2 is 3. 3 plus 10 is 13. So 13, again, this is in thousand. 13,000 people commute to work after the year 1980 for this. 6 years after the year 1980. B of 6 is equal to, I'm going to plug 6 in right here. So 2 times 6 plus 4, that's 12 plus 4, which is 16,000. Yeah. So which one is greater? B of 6. is greater. All right, solve the equation a of x is equal to 15 and explain what it means in the context of the problem. Okay, 15, they're telling me is an output, so I'm going to replace a of x with 15. I have 15 is equal to x divided by 2 plus 10. So first step here needs to be getting rid of this plus 10 using subtraction. So I have 5 is equal to x divided by 2. Now to undo division, I need to multiply by 2 on both sides. So x is equal to 10. Okay, so that's part of the answer. Now I need to explain. So remember, x is the years after 1980. If 10 is x, that means I need 10 years after 1980, which would be 1990. So in 1990, okay, we know that there were blank people that, okay, well, what is the context again? Right? Commute to work using public transportation. Okay, we know that blank people commuted to work using public transportation. Okay, and remember, we have two different cities here, so we have to specify. So in city A. Okay, this right here took care of the input. Okay, that took care of this 10. Now the output is this 15. So we know that there were 15,000 people that commuted to work using public transportation. All right, over here we want to select all the true statements. So the following graph is the rider's height in meters on a Ferris wheel. Select all of the true statements. Okay, vertical intercept. Again, this is vertical, so I'm talking about where it crosses the y-axis. So it's at 2 meters. Okay, well that looks to be about true, so that's correct. Okay, the vertical intercept shows the starting height or position of the Ferris wheel. Well, yeah, right, that is exactly what this means. It's the height on the Ferris wheel. The function reaches its maximum value after the first drop. Okay, well, maximum is right here. Okay, does this happen after the first drop? Well, that doesn't make sense, right? Here's the first drop, okay, and that's not where the maximum is, so that's not true. Okay, there are no horizontal intercepts. Okay, horizontal is this. So I'm looking at the x-axis, and it looks to me like it, it does not cross at all, so that would be true. There are no horizontal intercepts. Okay, the function has no minimum value. Well, that's not true, right? There's a minimum right here. There's a minimum right here. Okay. H of 10 is the maximum value. So they're telling me an input of 10. So let's go over to 10, follow it up to my graph, and hey, yep, that is definitely my max. Here, there are several times when the function hits a minimum value. Well, we already pointed out that there were 2 that have the same minimum, so that is true. And then it says the minimum value is 0. Well, you guys, if I follow this y over, the minimum value is actually 2, so that cannot be true. Right? And that's because, we don't want the roller coaster hitting the ground. That would be no bueno. All right, here, select all the following true statements about the graph. So they're telling me inputs and outputs, all of these fun things. So f of 10 is 20. So let's find the input of 10 and find the output. Okay, looks like it for sure is hitting 20. That is correct. F of 20 is 10. So let's go over to input of 20. Read the output. The output is 30, not 10. They're saying that the output at 30 of the input of 30 is the same as the output when the input is 35. So let's see if these y values are the same. So go to 30, go to 35, follow it up. Yep, they both have the same output of 50. So that is true. If I plug 0 in, I get 55. well, that's not true, right? 55 is way up here. But if I plug 0 in, I do in fact get 0. So that is true. All right, f of t is 30. That is telling me an output. Is that true when the input is 50? So let's go over to 50. Okay. And the output is like, I don't know, 12, 13, right? And that's not true, right? The output is not 30. Okay, the output is 30 when the input is 15. Well, let's go to 15. The output is indeed 30, so that is true. Okay. The output is bigger than the output of this. So look at the input of 25, figure out what the output is. Okay. Input 25, output is 30. Okay. Input 35, output is 50. Okay. Is 50 bigger than, sorry, is 30 bigger than 50? No. Okay. The output when the input is 5. So go to 5, output is 10. Input is 10, output is 20. Is 10 less than 20? Yes, that is true. Okay. Let's take a look at the next one here. All right, the table and graph show the number of people who own a cell phone in a city in thousands between the year of 2005 and 2015. Okay, so the first thing says sketch the graph. So let's just go ahead and plot these points. So at 2005, there was 1, and again, that's 1,000. 2006, 1.2, so like right there. 2007, 2.8, so like right there. 2008 is 3.4, so right there. 2009, 4.2. 2010 was right at 6. 2011, 7.4. Again, these are not perfect, but a general consensus. 2012, 7.6, so not too much of an increase. 2013 was at 8, so right there. 2014, 8.5, so right there. And 2015 was at 9.8, so almost up to 10. Okay, so it looks something like this. All right, and then you could go ahead and connect that if you'd like. So it looks something like that. All right, now it says find the average rate of change. You guys, average rate of change is the exact same thing as slope. Okay, you find it by doing y2 minus y1 over x2 minus x1. Okay, so find the average rate of change between the years of 2005 and 2015. So I'm just actually going to write these coordinates out. That way I can label them as x1, y1, x2, y2. So at 2005, the output was 1. So 2005, comma 1. 2015, the output was 9.8. Okay, let's just label these as our x1s, y1s. x1, y1, x2, y2. And let's literally just plug these into the formula. So m is equal to, so y2 minus y1 divided by x2 minus x1. Okay, pull out a calculator, so 9.8 minus 1 is 8.8. 2015 minus 2005 is 10. 10. And if you plug that in your calculator, 8.8 divided by 10 is 0.88. Now, it is super important that you need to include label in your answers. So, notice, the top was talking about the y, which is thousands. So, 1,000 people per, that's what I call this, is this line tells me per, and this simplified to be over 1. So this is 0.88 over 1 technically. And then the denominator was representing year, so per year. So that is saying that the average rate of change between 2005 and 2015 was 0.88 thousand people per year. So that many extra people were getting cell phones. All right, here the average rate of change, the average number of people with a cell phone between the years 2008 and 2011 is 1.0 thousand people with cell phones per year. If growth continues at this exact rate, in what year will there be 15,000 people with cell phones? Okay, the best way to do this, you guys, is to just create a graph. Sorry, not a graph, a table. Okay, so if this is the year, and this is the people with cell, okay, so we left off in 2012. That's going to be my starting point. And in 2012, we had 7.6 thousand people that had cell phones. Okay? Now, if it says we are increasing at this rate every single year now, we want to keep on going, follow that pattern until we hit the number 15. So let's go to 2013. Okay. So 2013, if I'm going to add 1.05, 7.6 plus 1.05 is 8.65. Okay. Then I have 2014. Again, I'm going to add 1.05 in 9.7. 2015 plus 0.5, 10.75. We got to keep going. 2016, so plus 1.05 is 11.8. 2017, keep on going. 12.85. 2018, 2019. I'm going to keep on following this pattern. Getting closer. Okay, super close. We're at 14.95. So 2020 we hit. So I'm going to keep on adding that 1.05. And I hit 16. Okay, so in what year will there be 15,000 people in this city with cell phones? Well, not quite in 2019. So the threshold of 15 got met somewhere in between here. So I'm going to say 2020. So in the year 2020, 15,000 people in the city will have a cell phone. Okay, now I'm well aware that these numbers, like from 2012 to 2015, don't quite match up here. That's okay. That's because I was telling you the rate to increase by. Okay, so this is a little bit different. All right, down here it says, how does the average rate of change between the years 2006 to 2009 compare to the average rate of change between the years 2013 and 2015? Okay, so I need to find the average rate of change for each of those. So I'm going to break this into 2006 to 2009. Okay, and then I'm going to do 2013 to 2015. All right, so again, I'm going to follow this pattern right here. So y2 minus y1, x2 minus x1. So 2006 has an output of 1.2. Okay. And 2009 has an output of 4.2. So I'm going to go ahead and label those as x1, y1, x2, y2. And plug that into my formula. So m is equal to y2 minus y1 divided by x2 minus x1. Right, so 4.2 minus 1.2 is 3. 2009 divided by 2006 is also 3. And 3 divided by 3 is 1. Now remember, include label, include context. So 1,000, okay, numerator's talking about people, so 1,000 people per, and then bottom is year. So between the year 2006 to 2009, the average rate of change is an increase of 1,000 people per year owning a cell phone. Okay, if I have 2013, the output is 8. If I have 2015, the output is 9.8. Go ahead and label those with x1, y1, x2, y2, and then follow our formula. So m is equal to y2 minus y1 divided by x2 minus x1. So 9.8 minus 8 is 1.8. 2015 minus 2013 is 2. If I take 1.8 divided by 2, I get 0.9. Again, include label, so that's 0.9 thousand people per year. All right, so once we found those average rates of change, we can now compare them. So what I would then say is like, it's not that much of a difference, but this one's a little bit more. So I would say the average rate of change is greater between 2006 to 2009. Okay, and then I'm going to talk a little bit about what this means. So an average rate of change being bigger, all that means is that the rate was growing faster. This means more people were getting phones. During this time. Okay, more people were getting phones during this time. All right, moving on to the next, we've got a bathtub here. Again, it starts with 60 gallons of water and it drains. Drains tell me it is decreasing, so I'm going to have a negative slope. Okay, it drains at 10 gallons per minute. Function W gives the amount of water left in the bathtub after m minutes. Okay, I almost think that it's easier to write the rule first before filling this out, to be honest. So function W is the name. The input, okay, is the number of minutes, which we said was m. And that's equal to, we have to figure out what an equation might be. So I like to start with what the initial value was. It started with 60. Okay, so 60 is what I start with. But then it's draining, so it's going to be subtracting whatever the rate is. So it's 10 gallons per minute, so it's 10 times the number of minutes, so 10m. That would be my function notation rule. So then I can hop back up here. If I plug 2 into this, I put it in your calculator. So I have 60 minus 10 times 2, and that's 40. Okay, and this is in gallons. Right? If I plug 4 in, so I have 60 minus 10 times 4, that would be 20 gallons. Okay? Now if I have m, it's going to be the exact same thing. It's just going to be what's over here. So 60 minus 10 times m, because I'm not sure what I'm plugging in. All right, so I'm going to go ahead and graph this actual function now. So the y-intercept is at 60, right? That's what I'm starting with at 0 minutes. And every minute it's decreasing 10. So I'm going to go down 10 over 1. Down 10 over 1. Down 10 over 1. Okay, keep on following that pattern. Move a little bit over here. So 3 goes up to 30, 4 goes up to 20, 5 goes up to 10, and at 6 minutes is when it is completely drained. Okay, and then if I were to take a ruler, it would look something like this. Again, it's not perfect because I grabbed it a little bit off. I just make that a little bit bigger. Okay, it should look something like that. All right, so show on the graph where W of M, okay, again, this right here is an output. So where's the output 40? I'm gonna go ahead and just circle that. So output are Y's, okay, this is where W of M is equal to 40, okay? And explain what this means in the context. Well, because when that happens, M is at 2. So that means that W of M is 40 when M is equal to 2. Now let's explain what that means. So M is minutes, the output is gallons. So after 2 minutes of draining, okay, the tub has 40, and then the output is in gallons, so 40 gallons of water. Okay, very last question here. We have area is found by multiplying base times height. A function a represents the area in square centimeters of a square with side lengths of x. Okay, so I'm going to call this x, 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 x. Notice a square has all congruent sides, which means the same. Write an equation that represents the function a. So if I were to plug 1 into this, okay, square with side lengths of 1, again, area is found by multiplying them together. So base times height. Area is 1 times 1, which is 1. Okay. Now, if I have a square with 2 as my side lengths, okay, base times height is 2 times 2, which is 4. Okay. Now let's say I have 3 by 3. Base times height is 3 times 3, which is 9. And then lastly, if I have 4 by 4, base times height is 4 times 4, which is 16. Now I need to write a function about how the input compares to the output. I notice that each time I'm actually squaring the input. Okay, so I'm going to say that a of x is equal to x squared. Now, if this had been a perimeter problem instead, right, I'm going to be adding all of these together, which would be 4x. So that would be for perimeter.